And now we will talk about the actual process for developing sound AI data acquisitions. So all the above contents in this seminar is prepared to understand this part actually. So as I mentioned before, the main goal of the sound AI is to make machine to listen like human is listening. So we want to understand the above path through the human ear and replicate it as for the robots. However, this figure is only for the understanding, and actual process is not that simple. So actual process is more like this. So when dog is barking, then there may be some walls which block and reflect some sounds, and there are another noise can be happened at the same time, like a sirens. When we listen and understand the dog barking sound, some dog experts can detect more detailed information. For example, is a barking sound or a whining sound, and how old the dog is, or is it Yorkshire Terrier or Greyhound. Can we understand the entire process of the human and can we replicate it for robots? It's really difficult, but that's what we are trying to make. So let's talk about every factors which can affect to the data acquisition process. First one is noise. The noise in sound is very different compared to the noise in the images. So when there is two objects at the same locations, normally one is occulted by another one. The cat which is in below the dog is partially visible. However, at least the dog is entirely visible in this figure. In case of sound, when there is a cat sound and dog sound at the same time, this is overlapped altogether, and this is really difficult to separate and understand individually. So we can think about this process as a sound addition process. Can we separate the first two sound components from the mixtures? So we need to develop some algorithm and the training system to reflect that behavior of the sound noise. Another important factor is reverberation. So reverberation is when sound is occurred in the room or near the wall. Path between the microphone and the sound source is not only one, but there can be multiple paths because of the wall reflections. There are many dog barking sound which is overlapped and delayed altogether. This is also similar effect when you shout near the mountain, then you will hear the echoes. This can be considered similar thing which is a blur effect in the images. So we can describe this effect like this. The original sound source is delayed and summed all together. And clipping is also happens when the sound is very loud and the microphone cannot capture the entire dynamic ranges. The dog is very big. I try to replicate this situation in the image domain. If the size of the range is limited, then we can only capture the very specific part, specific range of the object. So actually this is something similar effect with the overexposure in the camera. So if it is too bright or too dark, then it cannot capture the detail of the intensity differences in the images. Then what you can get is totally white image pictures, which is not that good. It can be described like this. So when the magnitude of the signal is really huge, then the microphone can only capture the very specific part and ignore the very high and the low part of the vibration. So of course the sound has some distortion because of that effect, which makes very uncomfortable sound effect to the users. It also makes the sound hard to be recognized by machines. Of course, when we record the sound by using different microphone, then all the quality of the recording is different, and it's also depending on the quality of the microphones. There can be some studio microphone and some microphone for karaoke or some toy microphone, and it all has different effects and different frequency ranges. When you make a sound AI machine which is trained by a very specific microphone, and if the user wants to use it by using different microphone, then it can make unexpected behavior. So actually there are so many factors to describe microphone characteristics, but I will not talk about the details in here. The point is, when we make a sound AI system, then we must consider about the generality, the robustness about the microphone. Of course, when the sound source is further or closer, it makes different effect to the sound recordings. Obviously, when the sound source is further from the microphone, it becomes more quiet, and the closer one sounds more louder. So first, when there is another noise, then the relative energy difference is depending on the distance of the target source and the noise. So when the target source is further, then the noise from the constant distance will affect more to the recorded data. When there is some high reverberation effect in the microphones, the closer one will have less affected by reverberation, because still the direct path between the source and the microphone is much closer than the alternative path. But when it becomes further, then the reverberation effect will be higher. And it's not about the microphone or some data acquisition, but it's also important to consider some context dependency when we collect the data. So let's say we want to collect gunshot data. We also have to consider that which sound can be easily confused with gunshot sound. For example, fireworks or some bottle open sound is very similar to the gunshot. When we say we want to make a sound AI model which can detect gunshot sound, it means that we want to make a sound AI machine which can detect the sound which is not gunshot sound. We also have a specific definition about the gunshot. We have a toy laser gun which has a very different sound, but it also can be considered as a kind of gunshot sound. Or some bazookas or some rocket launchers are also not gunshot, but for specific purpose or based on different context, also can be considered as a part of gunshot sound. What I want to say is it's really important to define what gunshot is and what gunshot isn't for every application. The process of developing sound AI cannot be achieved by a single team, but it's more like some collaboration of multiple teams all together. So here I briefly summarized what each team can try to improve the quality of sound AI. This is very rough idea, and basically that's why I prepared these seminars. If you have a good idea and if you have any suggestions, then please share into every team and to the company. We can try to improve the quality. So last part is signal analysis. After we collect all the data and then we need to analyze this information, sound AI machine can easily understand what this sound is. This is kind of some pre-processing part for send the sound information to the machine. The most simple way to represent sound is to represent it as some digitized numbers. You can see the vibrated patterns in the figure, and if we make a dot for every periodic moment in this vibration, then we can change this position of dot into the numbers. We can make this array of the digits, which can be considered as a digitized representation of the sound. Actually, this is the most simple way and used for all other signal domains like images. However, the problem of the sound representation is that this dot has very minimum information. If you pick one pixels of the images from the numbers, at least we can see how bright it is or how dark it is. However, the one single dot in the vibration means almost nothing, so we need to analyze the series of these dots, which means that the array has very redundant information. That's why I mentioned about some spectral representation before. So if we can summarize all of these periodic patterns into the one single numbers, it can be much representative and easy to understand. By using one dot in the frequency domain, then we can understand how low pitches the sound has or how high pitches it has. If we change this signal into spectral information, then we can understand in which frequency the signal mostly have. This can be considered as a good summary. However, the problem of the spectral representation is that we lost all the temporal information. The sound is kind of some temporal changes of the vibrations. We need to analyze these temporal dynamics of the sound to understand the context of the data. So we have an alternative solution to overcome these limits, which is dividing the entire time signals into specific parts and make a spectral representation for each segment. From this figure, you can see how the sound is changed from top to above. If we make very short segments and concatenate them all together, then we can see this kind of two-dimensional images, and we call it spectrogram. And again, we also want to apply the concept of the cochlea because humans have a really good ability for listening, so we want to mimic the process of how we are listening. One thing we knew from the human system is that human's ear has a different sensitivity for each frequencies. So we are more sensitive for the lower frequencies, and for the higher frequencies, then we are less sensitive. Some psychologists have experiments from the human participant, and the result is that from the figure, the different distance between the frequency informations is actually perceived as the same frequency differences. At the lowest frequencies, then the almost 800 Hz difference is almost same as 4,000 frequency difference in the higher ranges. Apply this concept to the spectrum, then we can make mapping tables for each frequencies ranges in the spectrums. So we can realign this information to the Mel scale spectrum. Lower part of the spectrum is more emphasized, and the higher part is briefly summarized. So normally we call it Mel scale spectrum or simply Mel spectrum. If we do the same process for the spectrogram to the Mel spectrum, then we can generate the right figures, and we call it Mel spectrogram. So Mel spectrum has several benefits compared to the waveforms, the normal linear spectrogram. So first one is at least we can get some information from each digit in here. Basically, it's a two-dimensional representations, so it can be considered as an images. Since there are lots of rapid improvements for the image analysis and image AI technologies, then we can easily apply that concept into the sound analysis process. Compared to the linear spectrogram, Mel spectrogram reflects human perception process very well, and practically it shows better performance in the most sound AI applications. These are also very important to understand sound AI, but these are not covered in here. We need to know the details of the human auditory system, so I only briefly introduce about the organ of the ear, but there are lots of some psychological process when we are listening some sound. Another thing is I skipped the most recent development for the sound AI. There are lots of actual deep learning architectures or strategies to train the sound AI systems. We also need to discuss how we can use this sound AI system in the real world. Thank you for listening, and if you have any questions, then please contact me.